Good afternoon. Welcome to the ZOOMTOWN experiment, episode number 46. Last episode we covered the creation of a trip plan, but the focus was more on the next step of that, creating the trip plan and then communicating it over to the Zoomie and all the mechanisms in that workflow. I also discussed about the trip plan, the codes, what they meant, and all of that information. Well, now we're going to take it to the next step or the next phase as the trip plan comes into the Zoomie. So that'll be our focus today. But I'm going to go down a quick side trip for a moment here. One of the things, and you might even have heard it in the background sounds of the intro video there with the Zoomie moving along. One of the problems I've had in a lot of the debugging and developmental tests is as the Zoomie's moving along, I don't really know if it's seeing a magnet or not because we've got embedded magnets all over the roadway. So I came up with a very simple and clever, I'll call it clever, way to deal with that. I changed the source code for the Zoomie, added another output, and I believe it was output 15, and then that was connected to a little buzzer. And I'd done a full video on that buzzer in the regular Pico series. So if you want to learn more about that cool little device, I'll put a link for that video in the description below. But anyhow, when I'm looking at the Hall effect sensors in the code, if I see a Hall effect sensor, I sound the buzzer. And that way, as the Zoomie travels along, I know exactly what it's seeing regarding the magnets. And from there, I can determine if things are behaving correctly or not. I just thought it was a way to solve a very complex problem in that I had no way to see it or understand if the Zoomie is detecting it in real time. So we'll run a quick video on that, show the Zoomie moving along again, and you'll hear him beeping as he sees each magnet. Pretty cool, huh? All right, now let's move on to what our main topic is today, dealing with the trip plan as it comes into the Zoomie. And I don't want to go into a heavy detail on the code. If you guys want to have an explanation on that, mention it in the comments below, and if there's enough interest, I'll do a code level review of that. But right now, let's just go to this screen here, and I will show you how we'll cover this. For today's episode. These are the different steps all the way through from receiving the trip plan to executing each of the motions. Our first two steps are to first receive the trip plan via MQTT / Wi-Fi, and then the function receiver callback processes that incoming data. Each time it receives a full trip plan segment bit of information, which is a full command. We will then convert that data into a list format so that it can be interpreted easier by another routine coming up. And that function is pack message to list. In other words, take that whole string of message data, put it into a list so we can work with the individual pieces of data within that string. And by the way, I will be sending out this source code or posting it. It's still riddled with a lot of debug information and a lot of bits and pieces of code that I'm experimenting with. So it's far from complete, but if you want to follow along and see what's going on, that's a good way to do it. Let me make this a little bigger here for everybody. This is the function receiver callback, a normal function that you utilize with MQTT communications. Anytime a message comes in, this function would be called. Here are some of the very simple ones that we communicate. E-stop or emergency stop, cycle start. That one I got to use every time I tell the Zoomie to go somewhere. Velocity override, that one's probably not used anymore. And finally, TP seg is the incoming message. And what that is a new trip segment. So in this function, I look at it, print out this message down on below here so I can see it in the shell, and then I pack that message to the list. That function is right up above. Here is that message. It's a string of data. We've got a global variable trip plan, and that's where we're going to write the information into. But here's how I use a function called message split. That separates up the little pieces of data in that string, and then I just take and pull all the bits and pieces and put them into each of the elements of the list. And this is a list of lists, just like everything else that we've been working with. And finally, we just add that in. And that's it in this area. So then we print out the data, just some information for me during debugging here. That would have been this function and this function. Now once we have the trip plan in the Zoomie, it doesn't just automatically start running that trip plan. There's usually a requirement for a cycle start to be pressed to make it actually do something. But right now the way I'm doing that is just temporary because I'm manually controlling that step. Because I need to debug the process and observe it better. But normally the scheduler would provide that cycle start button input, and then it would take off. Well, what's going to happen then, we're going to be running in the main loop. At this point, the list is complete, fully loaded into the Zoomie, and while the main loop is running, it will detect that that is there, that list of a trip plan. So in there, we're going to, in the main loop, we will run the executor function, and execute a function called execute trip segment. All that does is take the next segment of the trip plan and then tell the system to run it. So that performs that step, and then we go into the motion pre-processing. But first, before we go there, let's take a look at the main loop and then this step of the process, this short little function. Down here in the main loop, this is our main loop, 6 millisecond regulated speed. These are all the different things that get performed during the run of each run through the loop of the main loop. This one here, if trip status equals run, meaning it got that cycle start and the motion is currently stopped, we will execute a trip segment. And that would call this function. So that's up here out of the main loop, execute trip segment. Very simple function. As mentioned, we're going to print out a few things, and then with that, I'm going to execute the currently indexed trip plan pointer. That's a variable that just updates an index into our trip plan list. So let's take a look at that function at the top, which is way up here past a bunch of experimental code. And I'm going to get to this point here. Set MVC parameters, and we've actually covered this already on previous videos. But let me go back to our graphic list, and that's this function right here, and that is performing motion pre-processing. We've got our trip plan data, which is a set of instructions that are somewhat generic, meaning it will tell me heading and position and that sort of thing. But I need to convert that data into another set of instructions that will allow the Zoomie to actually move, because the trip instructions are kind of directions on what to do, but not the detailed instructions on how to do that. So that is this function of set MVC parameters. We'll go through this very briefly, and then after that we'll be back into the main loop, so we'll catch up on that in a minute. In the set MVC parameters, I've got a lot of global variables because I read and write and access these everywhere. This would have been a great example where making a class would have been better. Here I am just working with getting the data out of the trip plan from the list. Here's the pointer data to which line of the trip plan, and then these are each of the parameters, and I just simply write those into some local variables. Based on each of the different types of motions, we would have FLS, FLD, as we discussed last week. We will then take those parameters and set them into variables that are useful for that type of motion. Not all motions require all the various parameter settings. And then we calculate out a few other pieces of data that the motion controller will need in order to get from point A to point B, and things to expect along the way, such as distance to travel, distance to go, and getting other critical pieces of data set up for that motion. So we had FLS, FLM, very little data is needed out of that, just one parameter. FLD, that one only requires the distance pretty much, so we've got one parameter there. PID, pull into the driveway. That motion gets pre-processed and these variables get set. You'll notice a lot of these are all redundant. They're the same thing over and over again with only small variances along the way as to which other parameters are required. Back out of the driveway again, parameter 1, and our travel distance and all that. Finally, we've got a PTL, that is our pivot turn left. There you can see we've got a travel distance. We've got a parameter 1, parameter 2 that are being shown here, but those are used in this data as well. Finally, pivot turn right. That's the same as pivot turn left, except for when we're turning right, the left wheel's spinning, and when we're turning right, the left wheel spins, and when we're turning left, the right wheel spins. That's the big difference. And that information is here. Again, very straightforward. We're setting up a few parameters and just let it do its thing. And then we've got our very basic motion commands, BEG, beginning, and motion command, end. And that's just clearing out the trip plan and being prepared for the next set of trip instructions. So that's the pre-processing to really convert the trip plan data into useful information to perform that motion. Once a motion is processed through and everything is set with the set MVC parameters, within the main loop, I'm going to look for that and then execute that particular motion. So let's go take a look at that because that's in the main loop. Back at the top of our main loop, we're looking at our while loop, our regulated loop. This was where we called the execute the trip segment. And that's really still doing processing of the information. The trip doesn't actually start, or that motion doesn't start until it is called by this section. And this is just a series of if statements. If motion equals whichever one it is, FLS, FLD, etc., it will call out and execute that particular function, which now has the data from the previous steps to perform the motion. And that gets called every 6 milliseconds, so it's doing updating and processing of that whole trip, or that motion, every 6 milliseconds, because it constantly has to update. And then from there, we go back into some timing stuff down there. Once we execute the motion and we alert the system of one of the motions needs to be performed, then each one of these functions would be executing. Just as we got all of these commands, here are the related or associated functions that will perform it. And we've actually been through these in different forms and variations several times in the last few months, maybe a little longer than a few months. So we'll just kind of go over that in order in the code. And in this whole section of code from line 597 on down for several hundred lines is the action of performing each of those specific motions. For example, line follow steering with velocity correction. That's all of this code here, and that's the one that we use very, very commonly or frequently. Every time we're driving down a road with the marker tape and the magnets, we're running FLS. So all this code gets performed every 6 milliseconds so that our distance to goes and our distance traveled all get updated, as well as any velocity control things such as check and handle deceleration. There are certain times when I need to decelerate to a stop or decelerate to slow down for a turn. So that was that function. Here's our FLM function that performs our turning specifically for our sweeping turns on the bypass route. A lot of different things need to still be processed in here to further refine the data so that a proper motion can be performed. Pretty much a lot of the same thing as above, but using different components of the type of motion, using different sensors for what it needs to do. Here's FLD. Here's some code that was in there that I think I'm pulling out. But took all that and I think I condensed it down to just a few lines of code, which is part of this process, trying to keep the program compact. Our pull-in driveway function, that does a lot of different steps because we've got to take into account our cast sensor, how far it thinks we are from the barrier or the garage door. So that comes into play here, as well as encoder position tracking. There's a lot going on with that pull into the driveway that's outside of what we would be able to normally do with FLD. But nonetheless, the function, as you can see, other than a whole bunch of global variables, the actual work being performed is pretty much just this. It's very small and compact, but its behavior is very different from the others. Backing out of the driveway is very similar to pulling in. Obviously, we're backing out, though. And here we are with some PID control function on it. This is running encoder steering, so we can't use line following. So we do need that. And, of course, we are also using the cast sensor to detect how far we are from the barrier. And that's really a pretty important step when we're backing out of the driveway. When I back out and then I make that pivot turn, I want to be lined up on the guideline with my sensor. So that all has to play very tightly and very precisely. Early on, I kept emphasizing the importance of being able to position. My target goal was within 0.5 millimeter anywhere this thing moves or what it does. I don't think I'm ever going to achieve that goal, but I'm very close to it. And these are the different things that you have to do to achieve that precision. And hopefully I can get the rest of the little problems worked out. Here we've got our pivot turn left function. Very, very minimalistic there, right? It's mostly global variables, most of them probably not even really needed, but just to perform the turn. We're going to turn on the distance to go, let it do its thing, and that's it. The just run velocity actually does the work. Same thing with pivot turn right. Very, very simplistic. Just does starts its motion, performs it, checks the distance to go, and then when that gets to a minimal amount, then it'll stop or end that particular motion with a stop command. This whole process, and all that's happening every 6 milliseconds. So this little Pico W is really doing a lot of work over and over and over and over and over again. But as you see, right now it seems to be performing quite nicely. The Zoomie, for the most part, can get through from any place to any place with a fair amount of reliability right now. There are tweaks that I need to do yet, but I still haven't been able to fully understand the position, the reason for the positioning errors. So I've got a lot more testing to work through on that. But this should give you an overview of how the data, or that trip plan, starts over there on the scheduler software, gets over to here, and then how it's processed. And then that would just simply repeat over and over. At the end of a trip, it gets erased from memory. It's sitting there waiting for yet the next set of instructions, and then told to be started. So with that, I think we can wrap up this particular episode. And what I want to do is try to set the stage for what I hope will be the next episode. What I want to achieve next is, now I've got to communicate from the Zoomie back to the scheduler positional data, global positioning data. In other words, a coordinate relative to the entire layout, with the origin point being in the left side and far back corner of ZOOMTOWN. I need that information to be calculated. I got to put that code into the Zoomie control code. I need it calculated and as accurately as I can, and as, we'll call it, as current as I can, and then get that into the scheduler, which will then take that coordinate, take the sprite or icon of the Zoomie, and move it along the path that it's traveling. So I can see very close, or within 6 milliseconds of real-time updating of position. And then that's how I can then communicate to the Zoomie when it's stopped at a stop sign and it says, I'm stopped at a stop sign, when can I go? Give me the go signal. So that can then look over there. It says, okay, there's no cars on your road, go ahead and go. So that's a really critical step. Most of it seems to be seamless, but I've run into this thing where a whole lot of these simple things turned into an enormous amount of work. I'm hoping this one won't be too bad. At the same time, what I want to do, because we're getting very close to the end of code development within the Zoomie, I want to start going wireless completely. Take off the USB connection and just let it run wireless, and hopefully I can get things to behave the way I want and get the information I need to make corrections without seeing all the printed data coming out of the Zoomie. So that's my goal, get position data from Zoomie to the scheduler, and to hopefully go wireless for the next episode. So that'll wrap this one up. I look forward to seeing you in the next episode.